The key to this problem is understanding that the number of servers is equal to the number of SUVs in the fleet. Once you've identified that, we can treat this problem as we would other waiting time problems with multiple servers. To answer the first part, the number of SUVs parked in the lot, we must determine the utilization of the SUVs. The problem states that the average rental time is 3 days. This is our activity time, or P, but we're going to convert it to hours by multiplying times 24. A, our inter-arrival time, is given to us as 2.4, and M is equal to 50, or the number of SUVs in the fleet. We can then solve for utilization, which is equal to P over A times M. That's 72 over 2.4 times 50, or 120, which simplifies to 3/5. If we multiply that utilization times the 50 cars in the fleet, we know that 30 are being utilized, and the rest, the other remaining 20, are sitting in the lot. So therefore, the answer to part A is 20 SUVs. For part B, we'll calculate the utilization based on the new metrics and then convert this to an average revenue per day. Our new activity time is equal to 4 days, or 96 hours, and our new inter-arrival time is equal to 2, which is equal to the 24 hours in the day divided by the 12 rental requests per day, or 1 every 2 hours. M remains the same at 50. So solving for our new utilization, we get 96 over 2 times 50, or 100. Now, we know that based on that utilization, there are 48 SUVs that are being rented at any given time. Let's calculate a revenue estimate for part A. We knew that 30 SUVs were being rented on average at a price of $80 per day. That's average revenue per day of $2,400. In scenario B, we're renting 48 on average at a rental price of $55 per day, or $2,640. Based on that analysis, it makes sense to proceed with the pricing strategy as laid out in part B. For part C, we'll use the waiting time formula detailed below for multiple servers. We've already solved for all of these variables, so we can plug them into the equation. P, or the activity time, is 72 over 50 times the utilization, which is 72 over 120, raised to the square root of 2 times 50 plus 1, or 51, minus 1, all over 1 minus the utilization, or 48 divided by 120. That's times the CVA, which was given to us as 1 squared, plus the CVP. We knew that the standard deviation was 24 hours and the mean was 72, so that squared all over 2. Solving that equation, we get an answer of 0.019 hours, which can be converted to minutes by multiplying times 60, and we get 1.15 minutes. For part D, we'll again use the waiting time formula, but we'll need to recompute some of the inputs. Now, our inter-arrival time is equal to 3 hours. The CVA has not changed at all, however. P is now exactly 4 days, or 96 hours. CVP is equal to 0, however, because the standard deviation must be 0 if it's exactly 4 days. Now we can put these into the equation. The new activity time is 96 hours over 50 times a utilization of 96 over 150. This raised to 2 times 51 minus 1, all over the 1 minus the utilization, or 54 divided by 150. Our CVA is equal to 1 squared. As I said, CVP is equal to 0. All that divided by 2. The answer to this therefore yields 0.046 hours, which converts to a waiting time of 2.75 minutes for an SUV.